So the disk rotates about a fixed axis through O with an angular velocity of 5 radians per second and angular acceleration of 3 radians per second squared, which I've already marked into the diagram. So the small sphere A moves in the circular slot, and at the same instant we're given beta, beta dot, and beta double dot, and we're asked to determine the absolute velocity and acceleration of point A at this instant. Okay, so we're looking for VA and AA. So for this question here, we're going to need to use a rotating coordinate system to be able to solve it. Reason being is our ball that we're interested in is not like rigidly connected back to O like we've seen in many of the other questions. It's able to move within this slot. So what we're going to do is we're going to attach these coordinate systems, x, y here, onto the disk, and that's going to mean as the disk rotates, so too does our coordinate system. Okay. Alright, so the equation that we're going to use, we'll start with velocity. Is this one here. So our points of interest are between A, the ball, and O, which is the center of the circle. We're looking also at omega, r, and v rel, which we'll talk about in time. So let's go through and identify what each of these terms should be. So VA is the first one, and that's the one that we're trying to determine. So we're not really going to be able to do anything with that. I'll leave it as a question mark. The next one is the velocity of point O, and that's the center of the circle. So although the whole circle is going to be rotating round and round and round, the center point is not going to rotate at all. It's a fixed point. So it's going to have a velocity of 0. The next thing is omega cross r. And remember that omega is the angular velocity of the coordinate system. So since it's attached to the disk, it's going to be the angular velocity of the disk, which is going to be 5 radians per second. R, in this case, is going to be the radius of A relative to O, since we've got it written in this form. Okay. So summing this in, it's going to be omega for the disk, which is 5, and using our right hand rule, should have written that in, Z is out of page. So this is going to be a negative value, so negative 5k. And the radius of A relative to O, we're going to need to determine by drawing the triangle that sits in here. Okay, so this in here is beta, which we're told is 30 degrees. And we know that the length back to the slot, so the hypotenuse of the triangle, is 375 millimeters. This corner is A, this corner is O, and we need the radius of A relative to O, so it's going to be the arrow that way. And in X and Y, since that's how we've defined our axes, it's going to be those two vectors that add together. So it's going to be negative 375 cos 30i for the length of this line, and it's going in the negative x direction. The other one is going in the positive y, so it's going to be plus 375 sine 30j. So if you expand this out, it becomes this. Cool. Alright, so we've only got one term left for this velocity analysis, and that is a VREL. So this represents the velocity that you see when you're attached to the coordinate system. So if you're attached to the coordinate system, you're not going to see the rotational effects because you're rotating with it. All that you're going to see as you're standing on this point and looking out to point A is whether it's sliding within the slot. Okay? Again, you're rotating with this disk, so you're not going to see any of that rotational effect. So looking out at this point here, we're going to be able to calculate what the velocity is relative to the disk just by using the fact that we know that this here, the rate of change in your angle, B dot, multiplied by the radius, so I'm going to write it of A relative to point O, it's going to give you the relative velocity. Okay, So recall that we were given beta dot, the rate that this angle changes with respect to the disk. We're told it's 2 radians per second, and since we're measuring this way, alright, that is clockwise, it's going to go in as a negative value. So it's going to be negative 2 rads per second. Okay, so this is beta dot. And the radius of A relative to O, we already had that worked out back here, so we can just substitute it straight in. And again, we need to expand that out, so what we end up with is that there. Alrighty, so now we just need to go back and substitute all of these different things back into our original equation. So the velocity of A is what we're trying to determine. VO is 0. Omega cross R worked out to be this. And VREL this. Alright, so if you simplify that down, you come out with your final answer for the velocity of A in absolute terms. Okay, and the units are going to be in millimeters per second, since we measured all of our distances in millimeters. So that's one answer that we were looking for. And of course, if you wanted to, you could go through and work out the magnitude and direction of that, but I'm just going to leave it in vector form. So the other thing we were asked to do is find the absolute acceleration of point A, and it's pretty much going to be going through the same process except using the acceleration equation. So that one is the long one. That one there, quite long. Alright, so let's go through and work out each part again. So the acceleration of A is again what we're trying to find, so I'm going to leave that as a question mark. The acceleration of point O, it's going to be exactly how we justified VO up here. It's going to be 0 because it's the fixed point at the center of the circle, so it can't move at all. The next thing that we have is alpha cross R, and this is going to be alpha for our coordinate system crossed with the radius, and it's going to be the same radius as what we used before, of A relative to O. Okay, so alpha for our coordinate system is going to be the same as what alpha for the disk is, since they're attached to each other, and that's going to be 3 radians per second in the positive direction. So this we can write as 3k, and this is the radius of A relative to O that we already worked out before. It's going to be this expression in the bracket here. So expanding that one out, it comes to be that one there. Alright, next up we have this omega cross R. And remember, omega was the one for the disk since our axes are attached to it. And we were given that it was -5. And omega cross R, we actually worked that out before, so if you want you can steal the bracket. This is what we simplified it down to, okay? So just putting that straight in. So this comes out to be that. Alright, keep going. So the next one is 2 omega cross VREL. So 2 and omega was negative k is fine. And vrel we should have worked out as part of the velocity analysis above. So before we simplified vrel to be this expression here, so we're just going to put that in. And when we simplify this, it becomes that there. Alright, so we only have one left, and that is the AREL term. So this one here, we should be able to calculate again using the things we were given in terms of the angle beta. So if we scroll back up, so we were told that beta dot was 2 radians per second and beta double dot is going to be negative 4. So basically that means beta double dot is the other way around. Okay, beta double dot. So because we're looking at between O and A, it's rotating. What we're going to need to consider is the normal and the tangential components of that acceleration. Okay, so the normal component is going to be the angular velocity, which is beta, crossed with the radius. So it's going to be A relative to O, since that's what the angle is between. Okay, the tangential part, so alpha is the same as beta double dot, and the radius is A relative to O again. So substituting in, before we said that beta was equal to negative 2k. Oops. I think we already have this. We can go back and look for it. So we're looking for beta dot A relative to O. And it's this here. So we can just take that expression and put it in. Oops, sorry, I just copied the wrong thing, didn't I? It should have been this one. Cool. And then beta dot, double dot, sorry, this one here. Scrolling back up. So we know it's going to be in the positive direction, and the number that we were given for it was 4. Okay, so the negative in this thing I've already taken care of by drawing it back the other way. So we're going to put this in as positive 4k. And the radius of A relative to O we already had from before. So this can all be expanded out, and I'll just give you the final answer for that. Looks like that. Alright, so now we should be able to go back and put all of these parts that we worked out into our original equation and solve for the acceleration of A. So subbing it in, sorry Jay. We end up with that, and when you simplify this down, it comes to be about 14.6i take 10.5j, and this is in meters per second squared, so I just divided all of this by 1,000 because it was in millimeters per second squared. Alright, so there are our final answers for this question, for the acceleration of point A in vector form, and also the velocity of point A here in vector form as well.